Okay, in this video, I want to talk about how to add infinitely many things. So in the previous video, we talked about sequences, which is a list of infinitely many numbers. And I want to be able to describe like how you'd add infinitely many things. So here we go. Let's go. Okay, so infinitely many addition, it's called series. So we just want to try to add all the terms in an infinite sequence, A1 plus A2 plus A3 and so on. And there's a few different ways to write it. One way to do it is with this, right? With the summation notation of the name of the sequence AN, and the bottom index showing where you start with the sequence. And if you want to add infinitely many things, you write infinity on the top. If this is a finite number of things, then you write the last thing you want to add on the top of the Greek sigma. Okay. This notation does kind of get crowded. So it is actually pretty common if it's understood that you're going to add all the things, that you might write it like this. So with the summation notation with the sigma on the left, name of the sequence that you're adding on the right, and if where the n starts and where the n ends is understood, then you just write n. That's the bit index that you're adding over. Sometimes the textbook get even lazier and don't even put the n on the bottom of it. So if you see sigma and an, that just means you know from context which index we're talking about, it's n, and you add it all up. So that's what that means. Okay, so let's do an example of how to add infinitely many things up. So the first example is a nice one. We add 1/2 to 1/4 to 1/8 and 1/16 and so on. So that the pattern is clear. The denominator, what you're adding is the powers of 2, and see what it would add up to. So how do we know how to add finitely many things. How do you add infinitely many things? Well, let's first look at adding finitely many things. So we're going to create a new sequence called partial sums, where we only add finitely many things, right? So S1 consists of the very first term, 1/2. S2 takes the first two terms and add it together. So 1/2 plus 1/4. If you get a common denominator, you'll get 3/4 here. That's our S2. And so on. So S3 is the sum of the first three terms in the sequence. And S4 is sum of first four things. And the Sn is basically you add all the way up to the nth term. And you might see a pattern here: 1/2, 3/4, 7/8, 15/6. So it looks like the denominator is 2 to the n, and the numerator is 1 less than that. So that's what it seems like. At least the pattern shows. The first four pattern shows that. So let's see if we can do this right. Prove that that's the pattern, and what would be the limit. Okay, so what we'll do is the S infinity, basically, the whole sum is going to be defined as the limit as n goes to infinity of the partial sums. Now, we're not looking at the original sequence, an. An are the things that we're adding. We create a new sequence, Sn, a new sequence of partial sums. So these are the we add up everything so far, and then see if this guy has a limit. And that's what we're going to call the sum of infinite series. Okay, so it is a limit, so it might not exist. If the limit does exist, we say that the series converges. If the limit doesn't exist, maybe blows up to infinity, or if it jumps back and forth between different numbers, then we say it diverges. Okay, so let's try to add up things that we just kind of did. So we added 1/2 plus 1/4 plus 1/8. There was a really nice pattern of the each term that comes next was multiple. It was a power of something. So if you have that situation, it turns out that you can work out what the sum is going to be. So let's see if we can do this in general. So these things are called geometric series. Okay. They always look like this. So if you want to see if something's a geometric series, the first term in the sequence could be any number. We'll just call that A. And the ratio between the second term to the first term is going to be the ratio R. And then that gets multiplied each step in the sequence. And then you try to add them all up. Okay. So there's a couple different ways to write this depending on where you want to start your sequence series. So we have the first number A. It's the first term in the series, and you multiply by R to power of n minus 1 because R doesn't appear in the very first term. So we could say if you want to start n equals to 1, you have to subtract 1 from the power here, or equivalently, if you start the index at 0, then you don't have to do the annoying minus 1. You could just say a times r to the n because r to the 0 is 1 and it doesn't appear in the first term. Okay, right. So if you have a series like this, let's see if we can compute it. So the nth partial sum is going to be a plus ar plus so on until a times r to the n minus 1. Okay. What I want you to notice is that how similar this looks to r times the partial sum of Sn. So if you multiply each of these terms by r, all the terms are equal, except the first term is missing because you've now multiplied everything with r. And then you have one extra term at the end, a times r to the n at the end. But all the terms in between are exactly equal. So there's only two differences here. The first term is now missing, but the last, there's an extra term at the end. If you subtract each other, almost everything is going to cancel out, right? So what do you have left? So if you start with the Sn and subtract r times Sn, a doesn't cancel out because that's missing from the subtraction, but you subtract an extra term, a times r to the n. So this is an equation we get. And a nice thing about this equation is that you could just solve for Sn here. If you factor out the Sn from the left-hand side and divide by 1 minus r, we get a nice compact formula for the partial sum Sn. This is way better than this form because it doesn't have you adding hundreds of things, right? If n is large, this is a lot of addition. But even if n is large here, like even if it's 100 million, you could just compute this, right? The only work that you have to do is r to the n might be a lot of multiplication or exponentiation. But this formula is way better than what we had before. Okay, let's take the limit as n goes to infinity. Remember, when we looked at the sequence in the sequence video, we talked about what happens to large power of r. It depends on what r is. If r is between -1 and 1, if the absolute value is less than 1, then this thing gets smaller and smaller towards 0. If r is equal to 1, then it's equal to 1. If it's anything else, it diverges. So that's what it is for geometric series. If this goes to 0, what's left over is a times 1 over 1 minus r. So this is going to be the limit of the partial sums. So that's the limit. The first term divided by 1 minus the ratio of the terms from first to second. But note that this thing only converges if r is between -1 and 1, strictly between -1 and 1. When r is exactly equal to 1, notice that this formula doesn't make sense because we will get division by 0. If you think about it though, if r is 1, that means you're adding the same number a over and over. It's a plus a plus a plus a plus a, and so on. So if a is 0, then the sum is 0, but that's kind of stupid case, right? 0 plus 0 and so on. If a is anything other than 0, then as you add them, it's going to get bigger and bigger. So it doesn't converge. Okay, let's use this formula. So here's an example of an infinite series. Let's see. Let's see if it's geometric series, right? So if it was geometric series, the first term is 7 because that's what it started out as. And then the ratio from the first to second is -2/3, right? 7 times -2/3 is -14/3. And let's check if the pattern continues. So this thing, -14/3 times -2/3, so the negative will cancel out. The numerator is doubled, and the denominator is multiplied by 3. Flip the sign, the numerator is doubled, and denominator is multiplied by 3. So it looks like the pattern continues. So it's geometric. So what is the sum? It's going to be a divided by 1 minus r. So this formula works as long as r is between -1 and +1. So even if it's negative, it's fine. So that's 7 over 5/3. It's awkward. That's 21 over 5. Okay, so like 4.2 maybe. Okay, that's cool, right? Here's another one. Okay, maybe this might not look like a geometric series yet. Like if you can rewrite it in this form, it's either this form or that form. This is good. N starts at 1, so let's see if I can rewrite it as a times r to the power of n minus 1. So let me rewrite a little bit. So 2 to the 2n, that's the same thing as 2 to the 2 to the power n. So I can rewrite it as 4 to the n. And this is almost what we want, right? Like we want n minus 1, but we have 1 minus n instead. So what we could do is we can change the exponent to a negative. But if you do that, then the base is going to be the reciprocal. So instead, maybe write it as 1/3 to the n minus 1. So we're getting closer. What we could do is rewrite the 4 as 4 times 4 to the n minus 1. So I take out just 1 power of 4 here. And I did that because I wanted the exponent to be n minus 1. Okay, so we have a 4, and all of these have the exponent of n minus 1, so we can just combine it. 4/3 to the n minus 1. Okay, now it's in the form a times r to the n minus 1. So we know how to deal with it. Unfortunately, this problem has r that's greater than 1. So we have 4/3. So it's a geometric series, but we cannot use this formula. So the formula only works if the r is between -1 and 1. So this thing is divergent. Okay, so even though we put it in geometric series form, we know that it's divergent because r wasn't in the right interval. I hope that made sense. Okay, so there's one application that I really like sharing when I teach geometric series is to rewrite like a decimal expansion that you might get on a calculator. So everybody knows that if you're using a calculator and you get something like 0.33333 repeating, the answer is 1/3, right? But sometimes repeating decimals, it's difficult to work out what fraction it came from. But if you actually use geometric series, you could write it as a fraction. So for example, let's say you have a repeating decimal like this. So 5.1 is the non-repeating part. But after that, you get a repeating 232323 and so on. So whenever you get these repeating sequence of digits, it corresponds to a fraction. And how do we compute it? Rewrite it as a geometric series. So what you're gonna do is separate out the part that's not repeating. So 5.1 is separate. So we're just gonna put that to the side and rewrite the rest as a geometric series. So what can you do? So the next two digit is 23 or 23, but it's 23 divided by 1,000, right? Because the decimal place moved 3 places. So that's 23 divided by 10 to the 3. 10 to the 3 is 1,000. The next 23 is the same thing except divided by 100,000. You add 2 more digits of 0. And 23 over 10 to the 7th, and so on. So I'm breaking up each repeating 2, 3 as a fraction. Okay, so this is a geometric series. It has a starting number, and the ratio to the next one is dividing by another 100, moving 2 decimal places over. Okay, if you can write it in this form, we can now use the formula. So 1 over 100 is between -1 and 1. So we can use the formula. It's a divided by 1 minus r. And 5.1, we could also rewrite as a fraction, right? 51 over 10. And if you kind of multiply top and bottom by 1,000, you can kind of clean up this second fraction. It's the same thing as 23 over 990. And if you get a common denominator and add, you get that fraction. So this fraction is not something you're going to be able to guess, right? From looking at this repeating decimal. But if you use the formula for geometric series, you can work it out, which is kind of nice. Okay, so geometric series is nice, but there are other types of infinite series that we can compute. Another nice type of series that you might be able to compute is what's called telescoping series. So telescoping series is series that as you work out the partial sums, a lot of terms kind of cancel in between. So let me tell you, let me give you an example. So let's say you have a series like this. what we're going to do is we're going to first rewrite this as with using partial fractions. Okay. So what I'm doing is I have this fraction 1 over n times n plus 1, and we want to rewrite it in this form. So there's many ways to compute this, but one way to do it would be multiplying both sides of this equation by n times n plus 1. If we cancel the denominator, this is what we get. And 1 is equal to, let's see, if I collect like terms, there's many different ways to do it. So you could work out any other way to do it. So I'm looking at this, and the left and the right-hand side has to be equal. And this has to be equal for any n whatsoever. So that means that since n doesn't appear on the left-hand side, the coefficient in front of n must be 0. So a plus b has to be equal to 0, or that's another way to say a is equal to negative b. And the constant term a should be equal to 1, because that's constant on the right is a and constant on the left is 1. That should be equal to each other. So a is equal to 1, and that must mean that b is negative 1. Okay, so let's see if we can write down the partial sum. So the first partial sum is 1 minus 1/2. The second partial sum is going to be whatever we have earlier plus 1/2 minus 1/3. Okay. And the third partial sum is going to be whatever we had earlier plus 1 over 3 minus 1/4. Okay, I hope you're seeing the pattern. This thing nicely cancels out. Minus 1/2 cancels out with the 1/2 there. And negative 1/3 cancels out with the next incoming 1/3 there. So it turns out that everything in between cancels. What's left over is the starting 1 and the ending minus 1 over n plus 1. So in general, this is the partial sum. So we could actually take the limit as n goes to infinity of the partial sums. And 1 over n plus 1, that's going to get smaller and smaller. So we're just left with 1. So this infinite series adds up to 1 exactly. Okay, so that's a nice one. Here's another example. So remember, there's a log rule that says that if you have a fraction inside of the natural log, that becomes difference of the logs. Okay, and let's see what happens to the partial sums here. So S1 is going to be natural log of 2 minus natural log of 1. S2 is going to be natural log of 2 minus natural log of 1 plus natural log of 3 minus natural log of 2. And I'm going to jump to the nth term. Basically, the 2 will cancel out, and then the next 3 will cancel out. So you're going to end up with natural log of n plus 1 minus, what doesn't cancel out is the thing that starts out with natural log of 1. Well, natural log of 1 is 0, so we don't even need to write that. Okay. So natural log of n plus 1 is going to be the partial sum. We can take the limit here, and natural log gets larger and larger. So this thing does not have a limit. So even though it's a lot of things are canceling, that doesn't mean it always converges. This thing blows up to infinity. Okay. Okay, so a couple more things. Let's see, harmonic series is something that pops up over and over. So this is a very important infinite series. And basically, you're adding 1 over each integer. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. It turns out that this thing is divergent. And let me prove you why that's true. So the trick is to group things in powers of 2. So the first 2 things you're just going to group by themselves. So 1 is by itself and 1/2 is by itself. And the next thing you're going to group together is 1/3 and 1/4. So the next 2 terms you're going to group together. And the next thing you're going to group together is going to be 1/5 to 1/8. And then the next thing you're going to group together is going to be 1/9 all the way up until 1 in 16, 1 over 16, and so on. So the first 2 things are the exceptions. Those are the single groups. Then the next thing, you group 2 of them together, then the next 4, then the next 8, then the next 16, and so on. All right, so what does this grouping do to you? Well, what I'm going to do is I'm going to make this number smaller. So 1 and 1/2 I'm going to leave as is. Okay, so the next group, we have 1/3 and 1/4 here. I can make that smaller by turning them both into 1/4, right? Because 1/3 is larger than 1/4. If I replace 1/3 with 1/4, you're going to get something smaller. And the next group of 4 things from 1/5 to 1/8, I'm going to replace all 4 of those things with 1/8. Okay. And the next 8 things, we're going to all replace them with 1/16. You're just going to choose the smallest one in the group and group them all together. This is going to go off into infinity. Well, what is the sum of this thing? So you have 1 plus 1/2 plus, let's see, the next 2 terms is 1/4. So 2 divided by 4 is 1/2. And the next group of thing, there's 4 1/8. So 4 divided by 8 is 1/2. And the next 8 things is going to be 1/16. So 8 divided by 16th is 1/2. And maybe you see the pattern here. So each of the groups is going to add up to 1/2. And well, what are we doing? We start with 1 and we're adding a whole bunch of 1/2. So it's going to blow up to infinity, right? It's going to get bigger and bigger and bigger. So each group of 2 to the n that you add, you're going to increase the sum by half. So this thing is divergent. But remember what we did here. So we didn't compute the harmonic series. What we compared to is something that's smaller that still blew up to infinity. So harmonic series, the original series, is also infinity, right? Like it's bigger than infinity, so it has to be infinity. So this thing is divergent. This is the most important example divergent series that we're going to talk about. Remember this because it's going to come back. Okay, so one more theorem, and we'll call it a video. So there's one thing that you could use to detect some divergent series very quickly. So here's a theorem. So if the series is convergent, then because it's getting closer and closer to something, that each little thing that you're adding must be getting smaller and smaller, right? So if you have a convergent series, then the terms you're adding is approaching zero. So this is a very reasonable theorem. Okay. What this means is that we can look at it the flip side, right? So if limit as n goes to infinity is not equal to zero, then the sum cannot possibly converge. It's divergent. Does that make sense? So if the terms you're adding is not getting smaller, then there's no way the sum could converge. Right? So this is how it's used. So this theorem is sometimes called test of divergence. Right? But every time I teach this theorem, I have to always kind of give you a big warning sign. Okay, this can only show that something is divergent. So what that means is if the limit is not equal to zero, then it's divergent. Yes, we know that for sure. But just because it goes to zero doesn't mean it's convergent, right? So it goes one direction. So if it's convergent, the terms go to zero. But terms going to zero does not necessarily mean that it's convergent. So harmonic series is a good example here. So the terms you're adding, 1 over n, is going to zero, right? It's getting smaller and smaller, but it's still divergent. It adds up to infinity, right? So what this test of divergence tells you that if the limit is equal to zero, then you can't say anything about the series. If it goes to something other than zero, then it's definitely divergent. So you can sometimes tell it's divergent, but you can't always tell it's convergent or divergent. I hope that made sense. Okay, so let's do a few examples. From the last video, we know that the arctan goes to pi over 2. So the limit is pi over 2, it's not zero, so this has to be divergent. Okay, let's look at this one. If you divide the top and bottom by n squared, we get 1 over 5 plus 4 over n squared. So this gets closer and closer to 1/5, which is not zero. So it's divergent. Okay. This thing, 1 over natural log of n, well, this thing gets smaller and smaller. So this thing does go to zero. What do we know about this? We don't know. So could be convergent, could converge, or diverge. This test of divergence doesn't tell you if the limit goes to zero, it could still diverge. It could converge as well. So it's inconclusive. It turns out that this thing diverges, but that's using a different technique. So this theorem doesn't tell you one way or the other if this thing should converge or not. I hope that made sense. Okay, I think that's a long video, so let's cut it off here. I'll see you guys later.